Hi, my name is Joe Simon. I'm a postdoc at the Jet Propulsion Laboratory in Pasadena, California, and I'm a member of the Astrophysics Working Group. This video has been designed to introduce you to the ideas and the research currently being conducted in our group. So, how does the Astrophysics Working Group fit into NANOGrav? NANOGrav is a pulsar timing array, which is a gravitational wave observatory. This slide gives a general overview of how pulsar timing arrays operate. In the upper left-hand part of the slide, you'll see we have gravitational waves being emitted from cosmic compact objects. These gravitational waves perturb the space-time at the pulsars at letter B. The pulses from the pulsars then pass through the interstellar medium in part C and are observed by our telescopes at part D. We then take these observations, turn them into times of arrival, compare them to our model, and get residuals. These residuals are then searched for gravitational waves. The Astrophysics Working Group is particularly interested in two parts of the pulsar timing array observations. The first part is we're interested in understanding the source population. We do this through modeling and through various observational studies of the universe. The second major role that the Astrophysics Working Group plays within NANOGrav is helping to interpret the gravitational wave results. We do this by applying our models of our gravitational wave source populations to the results that we get. Now let's start by looking at how we understand our source population. Thanks to the incredible Nobel Prize-winning discovery of merging black holes by the LIGO collaboration, the era of gravitational wave astronomy has begun. Here I'm showing a plot of the masses of known black holes, both through gravitational wave observations and X-ray studies. The gravitational wave spectrum spans many orders of gravitational wave frequency, which is shown on the x-axis in this plot. On the y-axis is shown the gravitational wave strain, which is a measurement of the amplitude of the gravitational waves. The groundbreaking discovery made by LIGO was observed in this portion of the gravitational wave spectrum. In addition to LIGO's ground-based observatory, there are also plans for LISA, a space-based laser interferometer gravitational wave observatory. Both LIGO and LISA are complementary to the gravitational wave observations being done by pulsar timing arrays. Pulsar timing arrays observes binary black holes that are 1 million times more massive than those discovered by LIGO, and the binaries have orbital periods of years and/or decades compared to the orbital periods observed by LIGO, which are fractions of a second. There are many potential gravitational wave sources in the nanohertz gravitational wave frequency to which pulsar timing arrays are sensitive to. The primary source is expected to be a population of supermassive black hole binaries. But there may be other, more exotic sources, such as cosmic strings, which are topological defects which may have formed as the early universe cools. These strings can form loops and they radiate away their energy through gravitational wave emission. There may also be relic gravitational waves from inflation, which occurred during the Big Bang era. And of course, there are always unknown unknowns. However, for the rest of this video, we will be discussing binary supermassive black holes, their populations, and the gravitational wave that they emit. Our current best understanding is that galaxies form hierarchically, meaning that in the early universe there were smaller galaxies that merged to form the galaxies we see nearby today. This is a simulation done by the Illustris collaboration, which shows the formation of galaxies through mass buildup in dark matter halos. The left and right side of the simulation include different kinds of physics, but the general concept is the same. You can see galaxies emerging, AGN turning on, star formation starting, and all of this leads us up to the galaxies that we see at the present day. These simulations are state of the art and take many people and a long time to complete. In the local universe, we observe a link between the masses of central supermassive black holes and the galaxies that host them. Here I'm showing a plot of central black hole mass versus the velocity dispersion of the host galaxy. Thus, as a result of galaxies merging through cosmological time, we expect that the supermassive black holes they host grow this way as well. Now in this next simulation, we will see two galaxies merge. As the galaxies pass each other, they are disrupted, and the two galaxy cores quickly form a new bulge. As we zoom inside that bulge, we see the central supermassive black holes start to orbit each other. This process can take hundreds of millions of years. As the black holes get closer, they will start to emit stronger and stronger gravitational waves. And as the strength of the gravitational waves increases, the black holes lose angular momentum faster. Finally, as the black holes merge, we will now get a look at the gravitational waves being emitted. This process is happening all throughout the final phase of the merger, and there is a special gravitational wave signal that comes from the merger itself, which is called a gravitational wave burst with memory. Now, the population of merging galaxies is expected to give rise to a population of binary supermassive black holes, all of which will radiate gravitational waves during the final stage of their merger. This results in the formation of the stochastic gravitational wave background, which is the ensemble of all of the gravitational waves being emitted at the final merger phase of all of these binary supermassive black holes. The stochastic gravitational wave background is the primary gravitational wave source that PTAs are working towards detecting. The galaxy merger simulation I showed you earlier is a bit of an oversimplification of how the binary evolves from the galaxy merger process to becoming a loud gravitational wave source. The reality is much more complex. On the left here, I'm showing simulation results, similar to the ones that we saw earlier, and on the right appear some actual images of interacting and merging galaxies. Now, the reality is that these mergers take millions of years, and so we are stuck trying to piece together the whole picture with just a bunch of individual snapshots. Building these simulations is a bit like trying to recreate a dance from a series of still photographs. It's complicated, and there are many research teams using lots of hours on supercomputers to get a handle on this area of astrophysics. Now, the first stage that we saw earlier is the galaxy merger itself. Here we have a bunch of snapshots of a similar simulation like the one we saw earlier. Now, the process that brings the bulges together is called dynamical friction. And this is the gravitational drag that the supermassive black holes feel as they move through the scattered gas and stars of the merging galaxy. But once the new bulge is formed and the binaries are a bound pair, they need some other evolutionary mechanisms to get them close enough to where strong gravitational waves will ensure their eventual merger. However, this happens at smaller scales than these galaxy simulations can currently probe. These other evolutionary mechanisms are found in the new galaxy's core. The binary can interact with the stars and/or the gas in the new bulge, either forming a circumbinary disk by accreting gas, which is shown on the left here. The accretion flows apply torque to the binary and remove angular momentum from the system. Or, the more likely case in the largest of galaxies is what is shown on the right. You can see here the trajectories of stars in the galactic bulge. There is a certain subset of these stars that are on a trajectory that will bring the star close enough to the binary pair that it will get slingshotted out of the bulge and carry away with it a small amount of angular momentum. However, the stars on these trajectories will need to be replenished over time to make sure that this process can be sustained for the many millions of years it takes to bring the binary to a small enough separation where strong gravitational waves becomes the dominant binary evolution mechanism. And so finally, when the binaries get to that closeness, they emit strong gravitational waves. Here they are at separations of centi or milliparsecs. And that process will now quickly bring the binary to merger. However, if neither of the processes described in the last slide are present in the bulge, then the binary can potentially stall in something that's called the final parsec problem when it was first discovered. In the plot that I just pulled up here, part 1 shows the dynamical friction time, part 2 shows this environmental coupling time, and part 3 that here shows gravitational radiation evolution. And you can see that if that loss cone, which is the population of stars that are on a trajectory that take it close enough so that the binary will slingshot those stars out. If that loss cone, if that population of stars that can potentially be slingshotted isn't refilled over time, then the binary will stall and there won't be any mechanism to bring it down to the gravitational wave regime. However, if we neglect loss cone depletion, or we assume that the loss cone gets refilled through other mechanisms, which might be some kind of triaxiality in the galaxy itself, or some other kind of non-uniformity in the stellar densities that allow those trajectories to be constantly refilled, then the binary evolves relatively quickly from the dynamical friction time down to where gravitational waves become the dominant form of evolution. Now, we can put all of that together and we can build ourselves the stochastic gravitational wave background. Here I'm showing a typical model for the gravitational wave background. On the y-axis, we plot the characteristic strain as a function of the gravitational wave frequency shown on the x-axis. The typical power law shape here is a direct result of the gravitational wave emission being the primary evolutionary mechanism driving the binary throughout the pulsar timing array sensitivity band. The green region shows typical galaxy population uncertainties. These include uncertainties in the merging timescales, how long a merger takes, uncertainties in what the supermassive black hole mass relation is to various host galaxy parameters. The pair fraction is the number of merging systems there are in the universe, and all three of these are potentially evolving over redshift. As I said, this power law is a direct result from the gravitational wave emission being the primary evolutionary mechanism throughout the pulsar timing array band. However, it could be that the environmental coupling, the stellar scattering, or the circumbinary disk interactions actually continued to be the primary evolutionary mechanism or remain coupled to the binary into the pulsar timing array sensitivity band. And if that happened, there will be a deviation from this power law at low frequencies due to the more expedient evolution from those environmental couplings than just the evolution you would expect due to gravitational wave emission. Additionally, there could be an even further diminishing of the gravitational wave signal if there was any portion of the binaries that stalled, or if there was any other gravitational wave absorption mechanism, or if there was a really large offset between the masses of the supermassive black holes and the host galaxies that we are currently predicting. All of this encapsulates how we model and how we understand the source population for NANOGrav. Next, I'm going to talk a bit about how we interpret gravitational wave results using these models. Here I am showing some results from the 9-year gravitational wave background limit paper that NANOGrav produced last year. The dotted line shows the upper limit on the power law model for the gravitational wave background, while the solid line shows the per frequency gravitational wave limit. In the orange and inside the three thicker solid lines, you're seeing a prediction for the gravitational wave background amplitude at higher frequencies be applied to a generic turnover model. And you're seeing that our upper limit is actually informing the shape of what the background is based on that generic model. Currently, we can actually go one step further and map directly from the shape of the spectrum back to the environmental parameters themselves that are causing this change in spectral shape. Here I've just added some recent results. In the top right plot, what you're seeing is 4 different kinds of spectra. In part A, you're seeing a generic power law spectrum. In part B, you're seeing minimal environmental impacts, but highly eccentric binaries. The eccentricity of the sources can also impact what the shape of the spectrum is. In the slot number C, you're seeing a rapid in-spiral due to a very dense central bulge where a galaxy has lots of stars. And then D shows both a highly eccentric population and galaxies that have very dense stellar bulges. And below that, you're seeing limits on jointly the eccentricity and the density of stars directly from relating the upper limit that you're seeing on the left to the shape of the spectra predicted in the top panel on the right, and the blue and the red curves in the bottom right are showing you different limits on the joint eccentricity and density of stars based on various amplitude predictions for the power law gravitational wave background. These kinds of modeling, interpreting the results of the gravitational wave background is the primary purpose for what the Astrophysics Working Group is working towards currently. However, in the future, we will be working towards doing multi-messenger gravitational wave astronomy. In the plot here, I'm showing potential dual AGN gravitational wave sources and where they appear on the gravitational wave strain spectrum. So I'm plotting both on the y-axis the gravitational wave strain and on the x-axis gravitational wave frequency. You have different sources that are detectable as dual AGN. So these would be both emitting electromagnetic radiation as AGN that will be detectable as dual AGN, and there would also be emitting gravitational waves that will be detected by pulsar timing arrays. And we can lay on top of this our expected NANOGrav sensitivities for the future, and then looking even ahead to the coming decade to future radio telescopes. We can see here that the potential for multi-messenger gravitational wave astronomy with pulsar timing arrays is very strong. And we are currently working with many telescopes and many surveys to try to identify dual AGN candidates and begin the process of putting together a system to do multi-messenger gravitational wave astronomy with pulsar timing arrays. That's all I have. Thank you for listening, and if you have any questions, I look forward to speaking with you in the future. Thank you.